Lecture 1.5, Functions and Logarithms. This photo is the Golden Gate Bridge in San Francisco, California, taken by Vicki Kelly in 2004. And if you'll notice, down below the bridge is Fort Point, a pre-Civil War era fort built of red brick to protect the Golden Gate. A relation is a function if, for each x, there is one and only one y. A relation is 1 to 1 if also, for each y, there is one and only one x. In other words, a function is 1 to 1 on domain D if f of a cannot equal f of b whenever a cannot equal b. To be 1 to 1, a function must pass the horizontal line test as well as the vertical line test. For example, y equals 1/2 x cubed passes the horizontal line test because there is no place you can draw a horizontal line and hit the function more than once. So it is 1 to 1. The function y equals 1/2 x squared, which we recognize as a parabola, is not 1 to 1 because we can draw a horizontal line and hit the function twice. This horizontal parabola, x equals y squared, fails the vertical line test, so it's not a function. And it's also not 1 to 1. Inverse functions. F of x equals 1/2 x plus 1. We recognize as a linear function. We can write it y equals 1/2 x plus 1. Given an x value, we can find a y value. We solve for x, subtracting 1 from both sides, multiplying both sides by 2, and then moving the x out front. We then switch x and y, getting a new function, y equals 2x minus 2, which we write f inverse of x equals 2x minus 2. If we graph the inverse function, what we notice is that it's a reflection about the line y equals x. This is true for all inverse functions. Example 3, and this is actually example 3 from some book I had years ago. We have f of x equals x squared for x is greater than or equal to 0. We'd like to graph the original function f of x, also f inverse of x, and the line of symmetry y equals x for x is greater than or equal to 0. Parametrically on the TI-nspire, we'll press menu 3, 3, into the original function, x1 equals t, y1 equals t squared, for t is greater than or equal to 0. The inverse function, we switch x and y, so we have x2t equals t squared, y2 equals t. And you'll notice that for some reason I use different upper limits for t. Those don't really matter. We don't want to go to infinity, and we just have to be off the screen. And for the line of symmetry, we have y equals x, so x3 equals t, y3 equals t. Then we press enter, And we get the curves and the line of symmetry, although the equations are jumbled on top of each other at the moment. If we press menu 4:1, I'd like to zoom to a -1 to 7 by -1 to 3 viewing window. So I change my window settings. Press OK, so we get a little bit better picture of what's going on. Now notice that the horizontal axis and the vertical axis are not the same. So we want to fix that. We hit zoom for B, which is zoom square. That squares it up. And then we can move the equations to make it easier to read. We can also draw the same graphs by finding the inverse function. Starting with y equals x squared, where x is greater than or equal to 0. We can take the square root of both sides to solve for x, and then switch x and y to get the inverse function. So we have y equals radical x, which is f inverse x equals radical x. We clear the previous graph, but we'll keep the same viewing window. And we'll graph the curves as functions. So f1x equals x squared, such that x is greater than or equal to 0. f2x equals radical x. We can find, by the way, the vertical bar and the greater than or equal to symbol under the Control Equal menu. f3x equals x. And there's our graphs again. Consider f of x equals a to the x. This is a one-to-one function, therefore it has an inverse. The inverse is called a logarithm function. Example, 16 equals 2 to the 4th. So 4 equals log base 2 of 16. 4 is an answer to the question, 2 raised to what power is 16? The most commonly used bases for logs are 10, as in log base 10 of x, which we write log x, and e. Log base e of x is normally written ln of x. Y equals ln x is called the natural log function. Y equals log x is called the common log function. In calculus, we will use natural logs exclusively. We have to use natural logs. Common logs will not work. A few historical notes. Logarithms were invented by a Scottish nobleman named John Napier, who lived from 1550 to 1617. Logarithm is the combination of two Greek roots, logos, which means reason or ratio, plus artemis, which means number. The word logarithm was introduced in Napier's 1614 work, Mirifici Logarithmorum Canonis Descriptio, Description of the Wonderful Canon of Logarithms, originally published in Latin. Here's the first English translation by Edward Wright. Astronomer Johannes Kepler read Napier's work in 1616 and used logarithms in developing his third law of planetary motion. Kepler's third law states the square of the orbital period of a planet is directly proportional to the cube of the semi-major axis of its orbit. Kepler published the third law in 1620 in a book titled Ephemerides, dedicated to Napier. He later published his own work on logarithms. The term natural logarithm, actually logarithm Ephemerides us naturalis, was first used by an Italian mathematician, Pietro Mengoli, who lived from 1626 to 1686. Surprisingly, the notion ln for natural logs was not first used until 1893 by an American, Washington Irving Stringham, who lived from 1847 to 1909. In place of e-log, we shall henceforth use the shorter symbol ln, made up of the initial letters of logarithm and of natural or Naperian. Even though we will be using natural logs in calculus, you may still need to find logs with other bases occasionally. On the TI-nspire, you can find the log of any base by using control log. If you leave the base blank, it assumes you want a common log. For example, log 10 of 1000 equals 3. Or you can specify the base, log 2 32 equals 5. Here are shortcuts for accessing the various symbol palettes on the TI-nspire. The character and symbol key looks like a book. And it gives you various characters, including pi and e and I, and quite a few others. Expression templates. I don't have a good name for that key other than the expression key. Trig symbols. Or under the trig key. That one's pretty obvious. Pi symbols. These are just frequently used constants or variables. You may have noticed that the I, which is available here, was also in one of the other menus. I believe the infinity and the E were also. Equalities and inequalities are control equal. These symbols also could be found in at least one other palette. And punctuation marks. Here are some properties of logarithms. A to the log a of x equals x. Log a of a to the x equals x, where a is greater than 0, a is not equal to 1, and x is greater than 0. Since logs and exponentiation are inverse functions, they undo each other. The product rule, log a of xy equals log ax plus log ay. The quotient rule, log a x over y equals log a x minus log ay. And the power rule, log a x to the y equals y log a x. And the change of base formula, log a x equals ln x over ln a. These rules are still useful, but they were even more useful in the days before computers and calculators because they could change the more difficult function of multiplication to a simpler function of addition, and more importantly, they could change exponentiation to multiplication. It also allowed us to find fractional exponents. If $1,000 is invested at 5.25% interest compounded annually, how long will it take to reach $2,500? We have 1,000 times 1.0525 to the t equals 2,500. Dividing both sides by 1,000, 1.0525 to the t equals 2.5. We use logs when we have an unknown exponent. Taking the log of both sides, and you could have used common log, but since we're in calculus now, we're going to use the natural log. We can move the exponent out front and solve for t. Now we use our calculator to get an approximate answer, 17.9. So about 17.9 years. In real life, you would have to wait 18 years.